Good morning, students. In the last lecture, we discussed about the ideal gas, real gas, and mean free path. Now, we are going to discuss or derive a relation for pressure exerted by the gas on the wall of the container. We know that when a gas is closed into the container, there the molecules of the gas moving randomly within the container, and during this motion of the gases they can collide with the other molecules, and they also collide with the wall of the container. When they collide with the container, they exert some pressure on the wall of the container. Here we are going to derive the relation for the pressure exerted by the gas molecules on the wall of the container. Now here we are considering a gas. Now we can also consider here an ideal gas. An ideal gas can be obtained by maintaining the pressure and temperature of the gas. Now we know that the mean free path of the gas increases when the pressure decreases. So we adjust the pressure of the gas here such that there are no intermolecular force of attraction between them, and the collisions collision between them are elastic. So if the pressure of the gas maintained here, the real gas can be behaved as a ideal gas. So here we are considering a particular molecule, a single molecule of mass m, which is moving in a direction along the x-axis with a velocity v. Before that, we are going to define some terms which are very important for deriving this equation. Which are the terms? The terms, first term is the average velocity denoted by v bar. What is v bar is equal to? It is equal to v1 plus v2 plus v3 up to vn, and it is divided by n. We all know by this formula we can calculate the average velocity. Then we introduce a second quantity, mean square velocity. It is the mean of the sum of the squares of the velocity is divided by v square bar is equal to v1 square plus v2 square plus it is vn square, and it is divided by n. It is for the mean square velocity. And then we introduce here VRMS. What is VRMS? It is the root mean square velocity. What is that? It is equal to the under root of V1 square plus V2 square plus Vn square, and it is divided by n. So what is this value? Is equal to this. So we can write VRMS is equal to under root of V square bar, or we can also write this V square RMS is equal to V square bar. This is the important relation we need while deriving the equation for the pressure. Okay. So here we consider a molecule of mass m. It is moving with a velocity v in the positive direction of the x-axis. Okay. Now here we consider that the number of molecules along the x, y, and z axis are same. If there are n number of molecules, total number of molecules are n, then we consider that the number of molecules along the x-axis is equal to n by 3, along the y-axis equal to n by 3, and along the z-axis equal to n by 3. So suppose that the mass of the molecule we are considering here is equal to m, and the velocity is equal to v, which is moving along the x direction. So What is m? This m, it is nothing but the mass of the molecule. And what is v? V is the velocity of molecule. Now here we restrict ourselves the motion of the molecules along the x-axis. So here we taking the velocity of gas as a vx. It is the velocity of molecule along x-axis. So consider this molecule of mass S is moving with a velocity vx along the x-axis. Now we know if the particle is moving, if a molecule is moving, a momentum is associated with it. So we calculate the momentum. So suppose the momentum of the particle before collision is equal to P1 is equal to mass multiplied by velocity. So we can write here it is m multiplied by Vx. Now when this molecule travel along the x-axis and reach this phase, it collide with this wall and return back in the reverse direction. So after that the momentum is equal to minus v multiplied by x. Why this happen? Why this minus sign? This minus sign indicate that the velocity get reverse after the collision. So what is the change in the momentum? What is the change in the momentum of this molecule while traveling from this to this and here to here? Okay, so consider we denote that by px. X fall along the x-axis is equal to p2 minus p, which is equal to minus m Vx minus m Vx. So we can write here it is equal to minus 2 m Vx. What does minus sign indicate? This minus sign indicate that the momentum decreases by such amount. During the collision, this amount of such amount of momentum is decrease less when it return back to the original condition, original point, original position. So if this is the decrease in the momentum of the molecule, then here is this momentum goes, this momentum goes to the wall of the container. So we can say that if there is a loss in the momentum of the molecule during collision, then there must be increase in the momentum of the wall. So we can write here increase in momentum of wall is equal to twice m. This is the change in momentum of what? This is the change in momentum of the wall. Now what happened? Now we are going to calculate the force exerted by a single molecule, a particular molecule. For that, consider a single molecule which exert a force F1 on this wall of the container. And how the force can be calculated? This force can be calculated as the rate of change of momentum with respect to time. So we can write here this F1 is the force exerted by the first molecule on the wall of container, which is equal to F1 equal to delta Px upon T. Now how T can be calculated? Easy. This time, it is nothing but the distance divided by velocity. Okay, now what is the distance traveled by this molecule? This is the distance and again it return back to the original case condition. Then we can write here as a twice L, and what is the velocity? It is equal to Vx1 as we consider in the first particle. Here also we can write the momentum, change in the momentum of one due to the first one. So we can write this F1 is equal to, what is it? It is equal to delta Px1 divided by twice L upon Vx1. What is delta Px1? This delta Px1 is equal to twice N into Vx1 divided by twice L upon Vx1. So that is 2 and 2 get cancelled. So we can write here it is equal to M Vx1 square divided by. So what is this? This is the amount of force exerted by the first molecule on the wall of the container. So we consider here a large number of particles. Consider there are n number of particles. So we can write here this the total force Fn is equal to, what is equal to? It is equal to m by L in bracket is equal to Vx1 square plus the velocity of the second particle is equal to x2 square plus v square n, where this n is the number of molecules. So now from this force we are moving towards the pressure. Now what is the pressure? This pressure exerted by the gas on the wall of the container is equal to the force per unit area. That is equal to, this is the force Fn divided by area is equal to L square. So we can write here is equal to M divided by L cube is equal to Vx1 square plus Vx2 square plus Vn square. What is L cube? This L cube is nothing but the volume. So we can write here it is M by D. Now here we see what is this term? This is the root. This is the mean square velocity. How we can calculate this mean square velocity? This can be calculated as earlier. What is the mean square? It is V square bar is equal to Vx1 square plus Vx2 square plus Vn square, and this divided by n. So if this n is going here, here is n multiplied by V square bar is equal to, what is equal to? It is equal to Vx1 square plus Vx2 square plus Vn square. Here we are writing x because we are restrict ourselves along the x-axis. So this is n multiplied by Vx square bar is equal to this. So this term is replaced by this term. So we can write here this pressure P is equal to M divided by V into this n into V square bar. So this is the pressure exerted by the gas molecules on the wall of the container along the x-axis. Now by symmetry we consider that by symmetry we consider that Vx square is equal to Vy square bar plus or equal to Vz square bar. This all velocities are equal along the x-axis, y-axis and z-axis. And also we can write here as a v square bar is equal to, what is it is equal to vx square bar plus vy square bar plus vz square bar. So we can write here, if we keep the value of vy square and vz square is equal to vx, so we can write here it is v square bar is equal to 3 vx square bar. So we can write here, therefore what is vx square is p is equal to m by v into n into, it is 1 by 3 v square bar. So in simple way can write here it is 1 by 3, it is n multiplied by m divided by v into v square bar. So this is the expression for the pressure exerted by the gas molecules on the wall of the container. So in this way, by considering the molecule of mass m moving in the velocity vx along the x direction, we derive this relation in this way. So in the next lecture we derive the relation for the RMS velocity of the molecules. Is goodbye, have a nice day.